even be relics of days before there existed any universe as we know it. So, very people were very excited about this. So a lot of research happened in the meantime, okay? And then on the evening of October 15th, 1991, okay, a detector in Dugway Proving Ground in Utah detected the highest energy event ever, shocking astrophysicists worldwide. So this was really a megaparticle, tremendous energy. So just to give you an idea, so if you look in the popular press, this was called the oh my God particle. It was traveling at 0.9999. I mean, some of you can do this math here, pretty much at the speed of light, very close to the speed of light, okay? So if I were putting back, it's talking about my units of electron volts and joules, remember that 1 electron volt is approximately the energy that you get in a photon of sunlight, okay? So just go out in sunlight, approximately 1 electron volt. I'm talking about 10 to the 20 electron volts. That's how much energy there is in a baseball that you throw out, let's say at 56 miles per hour, 60 miles per hour baseball. So it's a tremendous amount of energy. What we know now is that a lot of research, which I'm just going to skip, is that these charged particles come from somewhere in outer space. Okay, they hit the Earth's atmosphere. They generate a shower of particles. And here's the particle zoo that I was talking about at the beginning that sort of is governed by standard model physics. Okay, and then experiments are, you put detectors on the ground in order to measure this. Okay, so measuring the highest energy cosmic ray is tremendous. So the amount of energy, again, to put this in perspective, if you were here for the Atlas talk, okay, so this is the Large Hadron Collider experiment that's in CERN. It's a particle accelerator. The energy I'm talking about here is about 40 million times more than that. So somewhere in the universe, we have natural accelerators that are producing this sort of energy. So this is very intriguing to us, and we really like to get to the bottom of this. And this has been one of the open questions in high-energy physics, in high-energy astronomy. What is the origin of the highest energy cosmic rays? And scientists have really done a great job, and this is not something that I've directly worked on, to measure the spectrum. So what you see here is a plot that basically is what we call a spectrum, which is nothing but a distribution of the amount of, in terms of the energy, what is the flux, or what is the amount of charge that's coming per unit area per second in your detector as a function of energy, again in these electron volt units. Okay, but the takeaway message here is that if you look at the highest energies, there have been several high-energy cosmic rays that have been detected. And in fact, the number, just to give you sort of a back-of-the-envelope calculation, it's about 1 particle per square kilometer per year. So it's not much. If you were to take Nevis grounds, maybe two times Nevis grounds, put a detector there, you'd have to wait a whole year to get 1 particle. So you really need large detectors or do something else to get these cosmic rays. Okay, so how do you get 10 to the 20 electron volts? How do you get somewhere? How do you get in the universe? What gives a kick? Okay, what sort of processes give you that much energy? What kind of particle acceleration goes on in the cosmos? So I'd like to talk a little bit about the kind of sources, okay, that produce high energy accelerations. So this is where I start talking about explosions in space, and there are several that we know about now. Okay. We know that energy is created from mass when stars explode. Okay. Here you see it's basically a visualization of what we call a supernova remnant. It's basically a star that's exploding. It's at the end of its life, and supernova herald the death of stars. So there are many supernova explosions, and we have measured these with other detectors, not just gamma ray experiments, with radio detectors, with optical, the Hubble Space Telescope. Gamma ray bursts, these are events, cataclysmic events that happen, episodic events. There's no way to predict when you can have a gamma ray event. There could be one, this instant. We have detectors trained to catch it. We just don't know when they're coming, but they're even more violent processes than supernova explosions. And then we have these objects called active galaxies, which is something that I work on myself. These are objects, these are galaxies that are active, unlike our Milky Way galaxy. These have supermassive black holes at their center, which power the emission processes in these objects. So we know that Einstein's equation, E equal to mc squared, everybody knows this. The famous equation of Einstein realized that mass and energy are equivalent and interchangeable.